Professor Thompson, and I'm going to go through some exercises from 3.7 and just go over L'Hopital's rule again. So I guess to begin, I will do some quotients. So, for example, this is number 5 in 3.7. So, the first thing you should do with any L'Hopital's rule problem is check if it is actually a L'Hopital's problem. So, this is e to the 2t minus 1 over sine t. The limit as t goes to 0. So what happens here is first you should just go ahead and plug in the value and see what you get. E to the 0 is 1, minus 1 is 0, and sine of 0 is 0. So it's not really 0 over 0, that's an indeterminate form, right? So that's why I put it in quotes. And the only time that you can use L'Hopital's rule is when you have an indeterminate form. So in this case, I take the derivative of the top and the bottom separately. You do not use the quotient rule, and then when you need to take a derivative, you do use the quotient rule. This is different. You have to think about the top and the bottom as separate functions who are racing. So they have their own derivatives. So the derivative of the top is 2 e to the 2t by the chain rule, and 1 goes to 0, and the bottom is cosine t. Now you should plug in 0 again and see what happens. Well, e to the 0 is 1, times 2 is 2, and cosine of 0 is 1. So now I can evaluate this and I get 2 to be the limit. Okay, so now let's do a problem that requires repeated L'Hopital rule. So this is number 6, and this is the limit as x goes to 0 of x squared over 1 minus cosine x. So again, immediately I plug in 0, and the bottom is 1 minus 1, which is 0, and the top is 0. So that's one of our indeterminate forms, so I can use L'Hopital's rule. So let me put L apostrophe H to indicate that I'm using L'Hopital's rule for this step. So x squared becomes 2x, 1 goes to 0. Cosine's derivative is negative sine x. I already have a negative, so I get sine x. If I plug in 0 now, I still get 0 over 0. But if this was the initial problem, I would tell you to use L'Hopital's rule. So just do it again. And the key way to notice that you should do it again is the fact that polynomials eventually go to constants. So polynomials always kind of disappear from L'Hopital's rule. So now if I plug in 0, I get 2 on the top and 1 on the bottom. So I guess again I get the answer 2. So you can do L'Hopital's rule as many times as it takes. Sometimes with trig functions or e, it'll go back and forth and it won't get anywhere, then maybe you shouldn't be using L'Hopital's rule. So in the case where you have a polynomial, though, polynomials will eventually go to constants. So now let's do a problem with a product. So the most common one is probably when you see trig functions. So for example, 26 here. This is the limit as x goes to 0 from the right of sine x ln x. And if I plug in 0, sine goes to 0, but ln, as you go to 0 from the right, is going to negative infinity. So that's basically the form 0 times infinity, which is indeterminate. So trig functions are your friend if you have a product because they're so easy to change into a quotient using the reciprocal trig functions. So I can make this ln x over cosecant x, and cosecant x is going to infinity on the right. So I still need to check that I have an indeterminate form because L'Hopital's rule requires you to have an indeterminate form of a quotient. So I get infinity over infinity, which is indeterminate. I guess technically it's minus infinity, but that's not really relevant. And now I can use L'Hopital's rule. And ln x becomes 1 over x, and cosecant becomes minus cosecant x, cotangent x. Now, what I'd like to do to simplify this is basically flip everything, because I can't quite tell what's going on. The top is going to infinity, but I don't know about cosecant and cotangent. I guess cosecant's going to infinity. So let's simplify. And let's put the trig functions back on top and put x on the bottom. So that'd be minus sine x tangent x over x. Now I can see that that is 0 over 0, because sine and tangent are both 0 at 0. However, the x will disappear if we do this again, although it is going to require the product rule on the top. So let's try that. So we'll go ahead and do that on the next slide. So our numerator is negative sine tangent. So if I use the product rule, let's just leave the negative out of everything. Sine goes to cosine. And then tangent goes to secant squared. And x goes to 1. Now, if I plug in 0 on the top, cosine and secant are both 1 at 0, which is okay, but tan and sine are both 0 at 0. So I basically just get minus 0 over 1, which is 0. So there's our product. Now let's do a difference. And again, we'll do a trig problem here, so we'll do 30. So the limit as x goes to 0 of cosecant x minus cotangent x. So you don't have a lot of tricks when you have a difference. The only real tricks you have are factoring, so you can make it a product, or common denominator is really your best friend here, because you have to make this a quotient. So to have a common denominator, you have to have denominators. And again, that's easy to do with trig. So let's write this as 1 over sine x minus cosine x over sine x. I could have written the second one as 1 over tan x, but that wouldn't be as good because this way I already have a common denominator. And so I didn't check if it's indeterminate yet because I don't expect you to maybe know the limits of cosecant and cotangent here. So instead, let's make it all a quotient and then check, because we know more about cosine and sine. So this is 1 minus cosine x over sine x. And so now if I plug in 0, I get 1 minus 1, which is 0 over 0. So it's indeterminate. And now I will use L'Hopital's rule. So the bottom becomes cosine x, and the top becomes sine x, because the negative goes with negative sine for the derivative, and 1 goes to 0. Now sine of 0 is 0, and cosine of 0 is 1, so I just get 0 here. So that was a difference, and the last thing I want to do is a problem with an exponent. So let's look at 37 here. It's the limit as x goes to 1 from the right of x to the 1 over 1 minus x. So that's somewhat of a weird exponent. If I'm coming at 1 from the right, then the exponent is very small and negative, so I guess on the denominator, so I guess that's all going to negative infinity, so I'm getting 1 to the negative infinity. But 1 to any infinity, that is indeterminate, whether it's plus or minus. So let's try to write this in a way that we can do L'Hopital's rule. So anytime you have a variable exponent and a variable base, you always use logarithm. That is your only trick. So the simplest way to explain this is that just like you can, if you have an expression, they always tell you you can add 0 or multiply by 1 for things like common denominator, because you don't really change it. Another thing to do is to write two inverse functions in a row with composition. So I can write e to the ln, because they cancel, of this thing here, x to the 1 over 1 minus x. And so that means that what's inside, well, let me write it slightly differently. Because e is continuous, I can write e to that limit. So I can put the limit inside. And what's inside here is a limit I can do because of ln. So all I need to do is do this limit inside the exponent, this big thing here, and then take e to that answer. So let's do that limit on the next page. So this is the limit as x goes to 1 from the right of ln of x to the 1 over 1 minus x. So the property of ln is that I can make the exponent a multiplier instead. So I have 1 over 1 minus x times ln x. So now let's write that as one big quotient. And so this is ln x over 1 minus x. And ln of 1 is 0, but so is 1 minus 1. So this has indeterminate form 0 over 0. That means I can use L'Hopital's rule, which I'll do on the next slide here. So ln x goes to 1 over x, and 1 minus x goes to minus 1. And I'm still taking the limit, so x goes to 1 from the right. And here I get, I guess, minus 1. But remember, that answer, that was the exponent, so I take e to the minus 1. Because it was e to that limit, I found that limit to be minus 1, and so the answer is e to the minus 1, or 1 over e.